Udah ya. Baik, selamat siang Bapak Ibu. Sebelumnya saya ingin menyampaikan bahwa acara sidang kita kali ini akan dilaksanakan dalam bahasa Inggris. Demikian agar dimaklumi. Before the dissertation defense is started, please set your mobile phone into silent mode, and it is not allowed to take picture or photo during this dissertation defense, except who had already had permission from SPSITB, since it will disturb its processes. Ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Greeting for all of us. I declare this dissertation defense is open. This dissertation defense is held to give opportunity to doctoral candidate Mr. Syed Saquib to deliver his dissertation research titled Enhanced Textile Dyeing Wastewater Treatment and Fouling Control Using Hollow Fiber Anaerobic Membrane Bioreactor and Downflow Hanging Sponge, and answer question or defend his dissertation against critics or comment in this session. Doctoral candidate has been doing his dissertation research under supervision of a team of promoters as follows. Professor Chandra Setiadi as Chief Promoter from ITB, Dr. Helen Julian, Co-Promoter from ITB, Dr. Sri Haryati Suhardi, Co-Promoter from ITB, while the examiners in this session are Dr. Ahmad Zainal Abidin from ITB, Professor Madetri Aripenia Krisnawati from ITB, Dr. Wiratni Budijanto from Gadjah Mada University. Ladies and gentlemen, next I will ask the Chief Promoter, Professor Chandra Setiadi, to deliver curriculum vitae of doctoral candidates and then to convey academic accountability regarding to the acceptance of this dissertation. Please, Professor Chandra.
Thank you, Chairman. So I will read the biography or CV of Mr. Syed Saquib. Syed Saquib was born in Varanasi, India on December 31st, 1998. With the parents' name is Syed Muhammad Mehdi and the mother is Anis Fatma. So Syed Saquib completed his schooling up to senior secondary level from Raj English School in 2015 and continued his bachelor's degree in biological and chemical sciences from Mahatma Gandhi Kashi Vidyapeeth Varanasi from 2015-2018. In 2018, he got selected in the top public university of India, namely Banaras Hindu University at Institute of Environment and Sustainable Development, to pursue his Master of Science in Environmental Sciences, especially in the ecological sciences, and graduated in 2020 with gold medal, or we call first rank holder. In 2021, Mr. Syed got selected at ITB under Ganesha Talent Assistantships in the International Fellowship to pursue his doctoral degree in chemical engineering until now. He got Best Doctoral Student Award 2023 from the Faculty of Industrial Technology ITB, and also became the recipient of the Kurita Overseas Research Grant 2023 from Kurita Water and Environment Foundation, Japan. So that one is the brief CV of Mr. Syed Saquib, and then I will read the academic accountability for the acceptance of the dissertation of Mr. Syed Saquib by the promoter team. Textile wastewater pollution has become a significant environmental issue worldwide due to this wastewater contain various toxic substances, of course, including the synthetic dyes. So the synthetic dyes is difficult to degrade and can harm aquatic ecosystem and also to human health. Conventional wastewater technologies such as biological, physical, and chemical treatments often come with a high cost and limited efficiencies, especially in addressing the complex toxic substances. So in this context, the anaerobic membrane bioreactors have emerged as an innovative and effective solution. So Mr. Syed Saquib's research introducing an approach in utilizing the hollow fiber anaerobic membranes with the offering several advantages such as larger surface area and also lower falling tendencies. As we aware that falling, it is the accumulation of the organic and also inorganic and other substances on the membrane surface. So the falling could impede the water flow. Of course, it is a major challenge in the membrane technologies. So this falling not only reduce the treatment efficiency, but also increasing the operational and maintenance costs. So in his research, Mr. Syed conducting in-depth studies on falling mitigation by controlling variable in fluxes. So that the initial flux, it means that refer to the water flow through the membrane at the beginning of the process. So that one, the initial flux will impact the overall system performances and the degree of falling. So his research aimed to identify how to get the optimal flux that minimize the falling, however maintaining the high treatment efficiencies. So moreover, Mr. Saquib explored the integration of the anaerobic membrane bioreactor with the downflow hanging sponge, or we call it DHS system. So this technology uses the porous media to support the microbial growth. DHS was utilized as the additional treatment aiming to address the toxic intermediate product, which cannot be degraded under the anaerobic conditions. So this combined approach is expected to overcome a more comprehensive and more sustainable solution for the textile wastewater treatment. So at the beginning, his research was conducted in the batch system or in the batch scale. So he tried to find the pH variation, how impacting the treatment efficiencies. So that this finding is quite important because of how he go through to select the pH, so that he come up that a natural pH was selected for continuous processes to optimize the removal of both color and also organic compound. So this compound, color, and organic is the main pollutant in the textile wastewater treatment. So and then subsequently he works on two identical system operated combination between the anaerobic MBR and also with the DHS, and operated continuously for more than 120 days. And then in the anaerobic MBR, they're working at the different fluxes. So that he found out that the high flux with the 56 liter per meter square per hour, or LMH, experience rapid falling due to the fallen accumulation. However, in the very low flux, 3.2 LMH, exhibited minimal falling. And then he found out that in moderate flux around 14.7 LMH, he successfully maintained the performances without sign of falling, even after 170 days of operation. Furthermore, the research also studied the role of the microbial communities in the textile wastewater treatment. The analysis showed that the certain microbial species, especially the Clostridium in anaerobic MBR, and also in the non-aeration phase in the DHS, play a very crucial role in organic carbon metabolism and also in the azo-bond cleavage. So the use of the DHS system with the intermittent aeration shows significant improvement in the effluent quality and also in the organic pollutant removal. In terms of novelties, his study offers several important contributions. Firstly, it is one of the few studies that deeply evaluates the impact of the initial flux in treating azo-dye wastewater treatment using the hollow fiber and anaerobic membranes. And secondly, he introduced the use of the low-cost DHS technology to improve the effluent quality with a very high pollutant removal efficiency. And third, his study provides a comprehensive review of the microbial communities, including anaerobic and aerobic microbes. So those microbes play roles in the dye degradation and also in the mineralization. Finally, also his research also includes in-depth study of the biofouling and analysis of the impact of the biofoulant into the system performances. So that one providing new insight into fouling mechanism and mitigation strategies. This research not only contributes significantly to technical knowledge in the field industrial wastewater treatment, but also has broad practical implication. So the use of the hollow fiber anaerobic MBR and the down-hanging sponge technology could become a more sustainable and efficient alternative for the textile wastewater treatment, with the potential application in other industries, not only textile. So the result has been published in international scientific journals, such as the Bioresource Technology Report and also South African Journal of Chemical Engineering. It is Q1. And also, he also authors of another 3 book chapters and co-author with 1 book chapters. So although that one also what has been done in his study. So he also presented in the various scientific conferences, both domestically and also internationally. So this demonstrates the reconnection of the academic and also industrial community toward the contribution to the research. So in conducting his research, Mr. Saquib demonstrated high skill in designing and managing experiments, data collection, analysis, and interpretation of results. The careful experimental design, accurate measurement method, and comprehensive discussion show high dedication and commitment in completing his research. This thesis not only meets high academic standards, but also make important contribution to the development of the cleaner and more efficient wastewater treatment technologies. Thus, this research is crucial in advancing the use of the anaerobic membrane bioreactors with the hollow fiber membrane and also combined with the DHS system for the textile wastewater treatment on the industrial scale. So this research offers a new and promising approach to more environmentally friendly waste management, which is highly needed in the modern industrial era that increasingly values of the sustainability and environmental sustainability. Bandung, August 13, 2024, promoter Professor Chandra Syed, PhD, and co-promoter 1 is Helen Julian, PhD, and co-promoter 2, Sri Haryati Suwardi, PhD. Thank you.
Thank you, Professor Chandra Stiadi. Now, could you please invite doctoral candidate to attend to this session? Doctoral candidates, Mr. Syed Saquib, are you ready? Are you healthy enough to perform this dissertation defense?
Sure, sir.
Okay. You are given opportunity to present your dissertation research in maximum 20 minutes. Time is yours, please.
Thank you so much. Bismillahirrahmanirrahim. Good afternoon to the respected chair, respected team of reviewers, and respected advisor and co-advisor, as well as dear participants. I, Syed Saquib, today going to present my doctoral dissertation on the topic Enhanced Textile Dyeing Wastewater Treatment in Hollow Fiber Submerged Anaerobic Membrane Bioreactor and Downflow Hanging Sponge. This is the overall presentation outline. Without wasting any time, starting with the introduction. So as we know that textile industry is one of the major economic sector that serves more than 8 billion population around the globe, and as well as producing around 56 billion and more than 56 billion kg of clothing and wearing apparels per year. But on the other hand, the problem with the textile industry is the excessive usage of several dyes, which eventually generate the excessive dye-laden wastewater and eventually harm the environment by human health as well as flora and fauna, especially in the aquatic environment. Among all the classes and types of the textile dyes, the azo dyes are one of the major dye used around the globe. They have the problem with the azo dyes that they are carcinogenic. They decrease the oxygenation potential in the aquatic environment. They have aesthetic problem due to the coloration, excessive coloration that they impart in the aquatic environment. And this is the basic structure of the diazo dyes or azo dyes. They are the main and major dye used globally with around 60 to 70% of the total dyes. The problem with the azo dyes is that they are stable and highly persistent among several kinds of processes and technologies for the treatment. Till now, there are several conventional technologies for the textile dyeing wastewater treatment. Among them, these are some of the conventional technologies. But the problem with these conventional technologies is that they have high operational cost. They produce excessive sludge generation after the treatment process. They consume high energy as well as they use excessive chemicals for the treatment process. So what are the technologies that we should come up with? So the solution is to come up with a technology that has low operational and capital cost as well as maintenance, as well as they have relatively low energy consumption overall. So to overcome this problem in this research, we took integration of anaerobic and aerobic process for the total dye degradation as well as the pollutant removal present in our textile dyeing wastewater. For the anaerobic process, we choose the hollow fiber submerged NMBR, anaerobic membrane bioreactor. The reason behind that, because they have highly efficient for the pollutant removal, they have low energy consumption as well as low capital and operational cost in comparison to other conventional technologies. For the aerobic treatment process, we choose the downflow hanging sponge, which is an emerging technology used in several kinds of wastewater treatment, and they use relatively lower aerobic or aeration or usually no aeration sometimes. For our research in aerobic bioreactor, we choose the generation 3rd type of sponge. Moving toward the problem statement and objectives, before going to objectives, this is the overall timeline of the research. In the stage 1, we first of all fabricate the batch reactor as well as the anaerobic membrane bioreactor, and we prepare the synthetic wastewater. We use synthetic wastewater in our research. In the stage second, we go with the batch reactor, and we check the effect of initial pH on the dye and pollutant removal, as well as the anaerobic sludge, the effect of anaerobic sludge on the overall dye removal in the batch reactor. Further, we move on for the continuous study using the hollow fiber submerged ANMBR. And first of all, we check the influence of variational flux as an operational parameter for the fouling control as well as the dyeing wastewater treatment. And we also done the toxicity assessment in terms of phytotoxicity using Vigna radiata seeds. In last stage, we go for the anaerobic system using integrated hollow fiber submerged ANMBR integrated with the downflow hanging sponge bioreactor for the efficient treatment of the dye wastewater. These are the problem statement, and the objectives are as follows. As I told earlier, the influence of variational flux was taken in consideration for the performance, wastewater treatment performance, as well as the fouling control. Microbial community assessment was checked for the role of azo-dye degradation microbial consortia present in our system. We also checked the effect of intermittent aeration for the efficient, for improve the efficiency of the integrated DHS with the hollow fiber submerged ANMBR, as well as we done the phytotoxicity assessment at the last. The novelties of this research is that we propose to use the hollow fiber module in comparison to other kinds of module because there are very few studies taken place and reported for the textile dyeing effluent treatment using the hollow fiber submerged ANMBR. We done the detailed fouling analysis as well as we come up with the aerobic treatment, low-cost treatment process. And at the last, we check the role of efficient dye-degrading microbes. Moving toward the material and methodology that used in this study. This is the overall diagram of schematic diagram of the hollow fiber submerged ANMBR and DHS used in the study. As we see that the working volume of the hollow fiber submerged ANMBR was 5 liter, and which was integrated with a 1 liter working volume of the downflow hanging sponge column. Next, in our study, we use the synthetic wastewater using a model dye named reactive black 5 or Remazol brilliant blue, black. And for that, we use the 50 mg per liter of our dye to prepare the synthetic wastewater. Now moving toward the detailed results and discussion. First of all, we check the biofouling mitigation under the influence of variational initial flux, operating flux in our hollow fiber submerged ANMBR. The operational conditions are as follows. We fabricate and operate 3 different reactors, reactor 1, 2nd, and 3rd, with different initial operational flux. The reactor 1 with high flux, around 56.92 or 57 LMH. Reactor 2nd with lower flux for 3.21 LMH, and median flux in the reactor 3rd, around 14.76 LMH, to increase the efficiency and permeate flow. As we see from the flux profile, the first flux profile of the membrane for the membrane performance in the reactor 1, which was operated at 56.92 LMH of very high initial flux, we could see from the very initial hour there is a rapid decline of the flux happened, and this could be due to this might be due to the presence to the accumulation of the foulant on the membrane surface due to the high initial flux. As well as, and after every HRT, we need to clean the membrane for the further usage or operation. Next, we go with the very low flux of around 3.21 LMH, and we could able to see that there is very less deflection from the median point or the around 1 of the flux profile. So, and there is a very stable flux throughout the operational period in reactor 2nd, as well as the reactor 3rd, which was operated at the very median flux of around 14.76 LMH. We again able to achieve a very high permeate without any significant fouling on the membrane. So we could able to say that the very high initial flux could impart the influence of the accumulation of the foulant on the membrane surface and clog the pore for the biofouling. From the SEM and EDX analysis, we could able to see that there is a significant accumulation and the cake layer present on the reactor 1 of high flux, and there is a significant lesser accumulation of the effluent on the reactor 2, which was operated at very low flux. And from the EDX analysis, we could see that the major effluent was of biological in nature, so the major biological effluent or biofluent was present on the surface. Conclusively, from the biofouling study, we could say that under the influence of variational flux, at very high flux, rapid flux decline or biofouling happened due to the concentration polarization on the membrane surface. Biofoulants were the majority of the foulants are of biological in nature, and the reactor that operated at low and moderate flux, having no significant fouling on the membrane surface, as well as the R2 and R3 both achieve the higher filtration rate or permeate flow. Now, moving toward the second major study that we done for the optimizing dyeing wastewater treatment or the pollutant removal from the in the hollow fiber submerged NMBR as well as the DHS column. First, again, we saw the influence of variational flux for the pollutant removal in our system, anaerobic system. We done this chemical oxygen demand study, and from the study, we could see that we could able to achieve 80%, above 80% COD removal by the end of the study under steady state operation. We could able to achieve the steady state operation by the end of around 70 to 80 days. There is significant fluctuation in it might be due to the toxicity toward the microbial or biological entity present in our reactor, as well as the fouling on the membrane. For decolorization, we done the spectral analysis as 597 nm, and we could able to achieve a steady state operation after the 30 days of the operation and able to achieve above 82% of mean decolorization or color removal. Based on the UV-Vis and GCMS analysis, we proposed a degradation pathway for RB5 dye, and under the influence of the anaerobic condition, first of all, the reductive cleavage taken place, and which generate or evolve the naphthalene and aminobenzene derived intermediates, which are much more toxic in comparison to parent dye. Further, under the influence of high HRT and the biological film present on the membrane surface, we could able to achieve a highly mineralized byproducts which having low toxicity. So toxicity which we will study further under the phytotoxicity analysis. Second, we also check the effect of intermittent aeration on dyeing wastewater or pollutant removal in our integrated anaerobic aerobic system. The operational condition are as follows. The study was done into 2 phases. The only difference in phase 1 and phase 2 is that the influence of aeration. In phase 2, no aeration was taken, and in phase 2, we give intermittent aeration in our DHS column only. From the result of chemical oxygen demand removal or COD removal, we could able to see that the reactor in phase 1, both phases, there are high treatment of the COD or COD removal taken place. But in the phase 2, where intermittent aeration was given, we could able to achieve higher pollutant removal in terms of COD removal. And the system was also become steady state. Similar result was seen in the for the decolorization using UV-Vis analysis as well as PTCO standard color unit method. We could able to achieve around 84.26% of the decolorization under UV-Vis spectral analysis. And for the PTCO method, by the end of the phase 2 under intermittent aeration, we could able to achieve the national standard discharge limit, that is under the 200 PTCO, and we could able to achieve around 151 PTCO color unit, which is under the national discharge limit. From the second major study, the conclusion, under the influence of variation flux, COD removal was above 80%. Lower initial flux reactor need prolonged stabilization period but could give efficient treatment by the end of the operation. Decolorization was also high, above 82 and 76% in both reactor 1 and reactor 2. And from UAVs and GCMS analysis, we could able to formulate that there is a formation of aromatic as well as the mineralized byproduct by the end of the overall study. Under the effect of intermittent aeration in integrated hollow fiber submerged NMBR and DHS, COD removal was exceed and until the 94.20%. COD concentration and PTCU concentration was under the national discharge limit of 150 mg per liter and 200 PTCU color unit. Next major study was on the role of microbial community and toxicity assessment. Under the anaerobic condition in hollow fiber submerged NMBR in reactor 1 and reactor 2, we could able to see that there is the increase of the Firmicutes as a major phylum from inoculum to the reactor 1 and reactor 2. On the term of the major class, the Clostridia increased significantly under the anaerobic condition, as well as for the genus, we could say that we could see that the genera Clostridium increased highly and significant under the anaerobic condition. It is due to because of its nature to persist and in the toxic environment and could able to achieve such results. From the result, we could conclude that Clostridium is the major genera and they are known for its hydrolyzing starch and also degrade azo dyes by the potential secretion of the azoreductase enzyme. Under the influence of the intermittent aeration in hollow fiber submerged NMBR integrated with DHS column, we could see that in the hollow anaerobic condition, the high abundance of anaerobic microbial community taken place, which further shifted toward the high abundance of the aerobic microbes in aerated DHS column. And these aerobic aerobic microbes are known for the amine degraders and amine and naphthalene byproducts degraders. Usually these are by Thiobacillus, Ephipia, and other aerobic microbes. Next, we done the phytotoxicity analysis in reactor 1 and reactor 2, working at different initial variational flux. And from the analysis, we could able to say that the reactor 2, which was at the lower initial flux, have higher toxicity in comparison to reactor 1. It might be because of the presence of the biofilm layer that we see using our semi-EDX analysis. The contact time for the microbes with the toxic dye stuff is much more in reactor 1. In comparison to reactor 2. So the toxicity level in reactor 1 decreases in comparison to the lower initial operational flux of reactor 2. Conclusively, we could say that the presence of several azo bond degrading bacteria or microbes were present in our both the anaerobic aerobic bioreactors. Major genera in both reactors were Clostridium, and which was further facilitated by the aerobic microbes and sulfate reducing bacteria for the total mineralization of intermediate products and total dye degradation. Phytotoxicity assessments shows that under the influence of high initial flux, the biofilm production was much more, or the formation was much more significant on the membrane surface, which leads toward the lesser the toxicity in our anaerobic system. Till now, overall conclusion from study, we could say that at the median operational flux of around 14.76 LMH, we could able to achieve high pollutant removal under the negligible fouling or membrane fouling at very low cost, longer operation. For a DHS system was established as a low cost and easy to set up post-treatment of the dyeing wastewater. And the integration of hollow fiber submerged NMBR DHS gives the best result under the intermittent aeration. For the major genera, Clostridium was termed as a major dye degrader or the major genera present in our both system, supported by the sulfate reducing bacteria as well as the aerobic bacteria for total dye mineralization. Future recommendation are as follows: that we need to come up with more operational parameter and to check like critical flux to for the dissemination of our such system into the real world scenario. We have to do the fouling mechanism as well as the modeling, fouling modeling studies. We need to treat the real textile wastewater in our integrated system to check its feasibility, as well as we have to go with a pilot scale first before translating our study toward the real scale. Techno-economic study should also be done. These are the research output in terms of conference paper and presentations. We could able to the outcomes of this result. This study was resulted into the publication of these two Scopus Index International Journal papers. And at last, I would like to thank the funding agency, especially ITV, for providing the Ganesha Talent International Fellowship, as well as the PPMI for the funding this project, and Kurita Water Environment Foundation for awarding the Kurita Overseas Research Grant. I would like to thank all the examiners, team of examiners, for their valuable time for reviewing the thesis, as well as I would highly thankful to my advisors and co-advisors for their constant support and encouragement throughout the study. And lastly, but not the least, that convey thanks to the staff and members and the students, especially master students, which worked with me during this period in MTB Lab, and my friends which present here today to support me. Thank you.
Thank you very much. Ladies and gentlemen, now we continue for questions and comments. First, I would like to ask our external examiner, Dr. Wiratni Budianto from Gadjah Mada University, to deliver question or comment. Please, Dr. Wiratni.
Thank you, Mr. Chairman. Congratulations, Syed, to come to this point at your doctoral study. You already presented your scientific finding very well in the dissertations and also in the presentations, and also already published in a very reputable journal. And I appreciate your effort very much in answering my questions, my review questions on the dissertation. It is very well answered. So my questions in this open exam will be more on the philosophical interpretation of your data to bridge your scientific finding into the potential applications of the research. All right, the first question, this is the general questions. I understand from the purpose of your research that one of your ambitions is to design an affordable or low-cost textile wastewater treatment.
Yes.
So based on your data, how you can, although I know you haven't conducted any techno-economic analysis study, but based on your data, can you infer the potential of your technology to be claimed as more affordable or more low cost compared to the existing technology?
Thank you so much for the encouragement and the question, ma'am. Yes, actually, in here, I didn't provide in the thesis the techno-economic analysis, but I done a little bit of techno-economic analysis also based on the hollow fiber NMBR treatment. And after the calculation of the OPEX on the operational expenditure, I could able to achieve like 0.11 meter cube per of the dollar per meter cube of the economy, which is much lesser in comparison to conventional technologies. For example, cars and other technologies, which are much more like 0.5 to $1 per meter cube of the treatment. So it's like some of the studies I done, but not in very much detail. So this will shows that its potential as a low-cost economic wastewater treatment study.
All right. To give me more descriptive, to convince me that this is really, really affordable, for example, for 1 meter cubics of the liquid, for every 1 cubic meter of the textile wastewater, how much fiber do you need for the hollow fiber reactor? For 1 meter cubic of the wastewater, textile wastewater, how many hollow fiber you need?
So for 1 meter of the fiber, actually, wait. Around
half of the volume,
half
or
of the volume, actually.
okay,
Yeah.
so Okay, and based on that information, do you think this technology can be applied for any scale of textile industries, for small scale to the big scale, or you suggest a certain range of skills that will best use this technology?
So for the translation toward the real scale, first of all, we should go with the small scale MSME to check its feasibility, because we right now also doing the real wastewater treatment study, and the sludge generation is too much. So we need to come up with a efficient cleaning strategy, which should not use too much chemical also. Although this tweaking with the operational parameter could able to achieve a very good result, as we see in our synthetic wastewater treatment also. So first of all, in my opinion, first we should go with the smaller scale, first pilot, and then smaller scale MSMEs like batik industry or something.
All right, yeah, I agree with you that it seems like this technology is more suitable for not too large volume of the wastewater, right? Because the hollow fiber will be enormous if you have to treat a large scale of textile waste industries. Okay, now the second question is about the overall data interpretations of your dissertation. Like I already asked you in the review before, your system is quite complicated because you have the hollow fiber anaerobic membrane bioreactor, and then it is coupled with the DHS, right?
Yes, ma'am.
So my question is, there are a lot of many possibilities that your dye disappearing in the system. It can be because of the anaerobic microorganism. It can be because of the adsorption on the membrane, adsorption on the biofilm itself, and then in the DHS reactor, it can also be because of the direct oxidations from the oxygen that you inject into the reactor. So my question is, how, based on your result, how do you determine which one is the most dominant aspect to degrade the azo dyes in the system?
Okay, so based on this research, as we see that the microbial activity is much more prevalent, like biodigestion activity, because the biofilm produced on the membrane surface is much more prevalent. If we see on the reactor one, we're having very high initial flux. So it is like simultaneous biodigestion as well as bioadsorption, then biodigestion, and then membrane filtration also. Because when we check with the just like DHS or just with the other aerobic technologies, the sludge is still there, the coloration is still there. So we need like simultaneous anaerobic as well as aerobic, and in these both system, biological activity are much more prevalent in that case.
Okay, so you are sure that it is the biological activity.
Biological plus the membrane also, because membrane could able to filter out all the pollens.
Yeah,
go in the permeate also.
Yeah, I agree with that, because you also prove that there is the breakdown of the azo dyes. So not only they are missing because of the adsorption, but it degrades even into the fatty acids. That will be my next questions. But now, before we are getting there, you are using synthetic wastewater, right, for this experiment? And based on your microbial assay, the dominant microorganism to break down the azo dyes are the Clostridia, right? My question is, in the synthetic wastewater that you are using, you put quite high carbon source from the glucose. It is around 1,000 milligram per liter, right?
Yes.
Which is quite high. Now, and Clostridia requires high carbon source because it is hydrolyzing bacteria. So usually they need high carbon source. So my question is, when we are using your technology to the real textile wastewater, where this carbon source will come from? Do you think the Clostridia will get enough carbon source from the textile wastewater alone without any additional carbon source from external?
So from the real dye also, we could see that the average of the carbon source in the real textile dye is also around 3,000 plus. Usually because of the high concentration of salt and other kinds of nutrient that used in the real wastewater also. So choosing the 1,000 mg per liter is like it's between like the.
That's conservative.
Yeah.
Okay, but in what form are the carbon source in the actual textile wastewater?
Sometimes acetate also.
Acetic,
Yeah.
acetic acid.
Acetic acid, in terms of acetic acid, in terms of some other carbon source also. Kind of.
But it is not glucose, right?
Not
Certainly
glucose,
not
actually.
glucose.
Glucose
So,
is, yeah, actually. Yeah.
so my question, why did you use glucose instead of the common or the possible carbon source usually found in textile wastewater?
So majority of the synthetic studies uses glucose. So I just choose glucose for like to check the role of microbes, which one is much more prevalent in that case.
I see.
Also like in real, the as I say that the concentration is much more high, even if it's like another forms of glucose, or sorry, another form of carbon source, the Clostridium is still present in real textile dyeing wastewater treatment in the systems.
Mr. Chairman, please let me know if my time is up. Do I still have time? 10 minutes. Only 10 minutes. I still have 10 minutes? All right. Okay. Next question is about the batch reactor experiment. It is the figure 1 in chapter 4. You mentioned there that for the batch reactor experiment, you can achieve 85% decolorization only for 1 day. So it is about 24 hours.
Yes.
Right? So my question, why do you still need more complicated reactor? Because it is already, we can do it in only 24 hours, and I think it is a huge achievement for azo dyes. So why don't you just go with the batch? Why do we need much more complicated reactor? And you need like 60 hours, right, for the
because
it is longer than the batch experiment. So how is your explanation about that?
So the batch reactor we use is very small, just 300 ml. So if we go for the further scaling of our batch reactor only, the more the accumulation of the dye is much more in there, and the flow is not, there is no flow at all, and we need more time in that case, because if the scaling, we scale up our system in comparison to continuous. And in the real system, in the real world, all the wastewater treatment are continuous in mode, basically most of them. So we need to come up such technologies which we could able to translate further on in the real world scenario also. So this is the we could achieve a very high percentage of the results in terms of pollutant removal and decolorization, but the scale is very small for the batch. It is just to check the effect of pH and the anaerobic sludge in that case.
I see. All right. The next question is about your hollow fiber reactor. I learned from your dissertation that the biofilm deposit is quite fast on the surface of the membrane, right?
Yes.
But biofilm has advantage for immobilizing the microorganism, so you will have a longer solid retention time. But on the other hand, it can also become additional barrier for the liquid to go across the membrane. So in this case, if I understand correctly from your presentation, biofouling, so the negative effect of biofilm is higher than the advantage, right?
Yes, ma'am. Yeah, because even at the very low initial flux and the moderate initial flux, we could able to achieve the steady state after a certain period of time, and we could able to achieve the similar results as we see for the very high initial flux operated reactor, and without any negligible fouling on the membrane surface.
Does it mean that hollow fiber reactor setup is not suitable for this case? Should we use another anaerobic reactor scheme to avoid the difficulties of biofouling?
Fouling is the major study done in this study is to mitigate the fouling using the operational parameters. And if we compare the hollow fiber membrane reactor with other types of membrane reactors, as well as the other type of anaerobic technologies for the wastewater treatment, it has much more efficient results and much more like possibilities of total dye degradation in comparison to other. So that's why we choose the hollow fiber membrane among all other membrane bioreactors. And fouling is the major challenge that we able to mitigate somehow using operational parameter. That's why my recommendation is to still go with the hollow fiber membrane for the longer operational period. Just we need to do more detailed study on the operational parameters, more operational parameter like critical flux and other, to make it more feasible.
Yeah, the reason I'm asking is because when you answer my first questions, you mentioned that the biological activity is more important.
Yes.
So I infer from that answer, I infer that it means the membrane filtration is not really very important in the setup. So why did you insist to use the membrane? If you just need the microorganism activity, then you do not need the membrane, right? You can use any other setup without the membrane, so you can avoid the biofouling.
Actually, we could able to use other kind of like USB and other kind of also, but the problem with like the starting point, the starting period of like USB is much more higher in comparison to the membrane system. So this is one of the advantage. Secondly, using membrane system could able to filter out some other kinds of like foulant, some other kinds of protein and carbohydrate in terms of foulant, and the biological biofilm activity that the extra exterior barrier that made on the membrane could not able to made another kind of like anaerobic technologies. That's why we insist to use the membrane reactor with the biological activity.
All right. And then the second thing that I'm interested in your hollow fiber reaction design is that you claim there was mineralization, so that your end product is the undangerous fatty acids.
Yes.
But you will need a dominant Clostridia species in that. So when we apply this in the real textile wastewater, do you have any suggestion how we can enhance the how you can enhance the growth of Clostridia so that it can be dominant, or we just let it be and it will automatically dominate the system?
Actually, it is automatically because in this research we use the sludge taken from the wastewater anaerobic wastewater treatment system from the outside, and as we see, let me show the wait. If we see the role microbes here, yes, in inoculum there is almost nil, almost no Clostridium at all. So Clostridium is much more have ability to adapt in the highly anaerobic condition as well as highly toxic condition. So it could able to proliferate itself when we use some of the raw sludge from the anaerobic or conditions in comparison to other kind of microbes. And further, the results and the possible result that we could able to achieve the high mineralization is because of the further support from the SRBs, sulfate reducing bacteria like D-sulfovibrio, solidosulfovibrio. And from the past research, it is already established that sulfate-reducing bacteria have ability to degrade naphthalene and benzene or aminobenzene products. And so that's why we could able to achieve the high mineralization, and the degradation of the intermediate products that formed after the degradation of the azo bond of the RB5. So it's not just Clostridium, but we need like such other supporting microbes also, like aerobes. That's why we go for the aerobic system also. And in anaerobic system, we could able to achieve such result by the support of the SRBs.
Okay, that brings us to the last questions from me about the DHS reactor. The role of the aeration is very important, right? In this DHS reactor, how do you quantify how much we need to inject the oxygen to get the correct composition of the bacteria?
So it's not based on the just composition of the bacteria. Before starting, we acclimatized our system for a bit with the aerobic sludge. And then we start with the normal aeration, like 2 liters per minute for 5 minutes on and 5 minutes off. Because if we continuously given the oxygen, then there is no need, the cost is exceeds, the operational cost will exceed. And from the past research, we see that the DHS column used with another type of anaerobic system, they could only achieve around maximum 75% of the total decolorization, and sometimes just 45 and 50. But in our case, we could able to achieve like above 82%, 86% by the end of the, if we see for the UV-vis spectroscopic study, and if we, for the PDCO, we could able to achieve the national standard discharge, below national discharge limit. So the aeration is based on the past research as well as the which used like aeration in their system.
So the consideration of aeration is more on the economic
Yeah,
side.
actually, yes.
Isn't that because of the consortium that the mix between the facultative microorganism and some aerobic, so you need both to survive so that you make intermittent?
Like we could see from this research, we could that there is a shift from the anaerobic to aerobic when we give like here, no aeration is given, and when the aeration is given in the middle part of the DHS column, the concentration of the aerobes increases significantly, and due to the sponge itself as well as the concentration of the abundance of the aerobic microbes, we could able to achieve high results.
Okay, thank you, Mr. Chairman.
Okay, thank you, Dr. Wiratni. For the next question and comments, please, Professor Penia Krisnawati.
Thank you so much.
Okay. First, I would like to congratulate you on finishing this dissertation.
Thank you so much.
And for answering all the questions that I asked you during the reviewing process and improving this manuscript based on my comment. And the question that I would like to ask you in this event is more or less beyond that. So relating your lab scale research to the application of this research. Since Dr. Wiratni already asked you about the microbial population, I would like to continue on that. So this graph and the previous graph that you show indicate that the analysis of microbial population that you did show a tendency of some microbial dominance, and there is kind of natural selection of the microbial species that active in the process. It's interesting to see that at first in the inoculum there is almost none Clostridia exists in the inoculum, and after the first reactor and the second reactor, Clostridium became the most dominant general of here. So my question is, it seems that the types of inoculum that we use in this wastewater treatment does not affect the performance of the process. What do you think of that? And what will be your suggestion? Which type of inoculum to be used? Yeah, if it is not affecting the process. Yeah. And the next question is, because Clostridium seems to be the dominant, the major species or genera in this process, what is your suggestion to maintain this dominance so that the process can go very well, yeah? Not disrupted by some kind of accident or something? Thank you.
Thank you so much for your questions, ma'am. So for the first question, based on the types of inoculum, is it effect or not? So in this research, we use the anaerobic inoculum from anaerobic wastewater treatment plant, and we just put in our, like, acclimatize for like around 3 weeks for that. So I think there is a bit effect of the, from the initiation point of view, from which type of inoculum that you going to use first of all. Although in the both of these reactor, the inoculum is typically same, but when the changes in the inoculum is based on the operational parameter. If you need to make the inoculum prospective or to match with the our technology, we need to change the operational parameter. For example, in anaerobic there is no aeration at all. So in anaerobic condition, the dominancy of the Clostridium exceeds because of its of the high concentration of the carbon source, as well as its toxicity, as well as its tolerance of the toxicity in case of dyeing wastewater. Secondly, we could say that these are the parameter. The operational parameter is the main thing which could able to achieve such kind of the anaerobic or aerobic microbial consortia in our system.
Okay, so following up your statement, I would like to further ask if the operational parameter is the major thing that affect the consortia of microbial in the process. So once again, the type of inoculum should not be matter, yeah?
Not that much. Actually.
Not that much, but basically we can use any type of inoculum.
Yeah, but it should be matched. Like for example, we take from a dyeing wastewater treatment industry effluent, like the sludge from the dyeing industry, and so it already have some kind of like microbial species which could proliferate in such environments. So.
And the next question is still related to that. In the operating the hollow fiber membrane anaerobic bioreactor, we also see that there is different performance that was shown by the different initial flux that applied. Interestingly, your data show that the lower initial flux applied to the system, the slower the process performance, or we can say that the slower the startup process to achieve a stable process performance. How can you relate that with this inoculum composition and also the natural selection, or is there a way to improve that based on the operational condition that you mentioned earlier?
Okay, so the thing is that at the very high initial flux, the flow or the permeate is too much high. So all the constituent like the foliant also accumulate so quickly, and that could able to accumulate the microbial biofilm on the membrane surface itself. So in comparison to the high flux, the median and the low flux need some stabilization point or stabilization time to achieve such results. This is due to the again the consortia could not able to make on the biofilm could not able to make that much significant on the membrane surface. That's why the membrane itself also needed for the and also the flow because the flow rate also is another parameter that could able to give the such results of the high concentration of the microbial biofilm on the membrane surface. So these are some of the parameters that we need to check for the enhanced working or the actions of the microbial consortia itself. That's why we need to put more pressure on the designing such system with efficient operational parameter.
Still related to that, I would like to ask, because the microbial activity in the treating the wastewater, the azo wastewater here, is generating the EPS and their related derivative products. Interestingly, if you imply a high initial flux, this EPS will induce the, what do you call it? The fouling. But the same EPS that was produced by the microbial activities in lower initial flux did not induce the fouling.
Yes.
How can you explain this phenomena?
Because in the permeate of the reactor second and reactor third, which is operating at the lower and median flux, we could able to see the concentration of the EPS protein and SMP protein and carbohydrate much more in comparison to R1. So the flux rate itself regulate the accumulation of such particle so quickly. So it's like a cake formation happen on the membrane surface of such EPS and other kind of foullants, which is not that much in case of reactor second and reactor third. That could be able to filtered out using from the membrane surface because of less concentration or the same concentration, but going to permeate in very quickly in comparison to the reactor 1. So that's why the EPS is much more on the reactor 1.
So let's say that the same EPS are generated, but in the lower initial flux, it is kind of soluble.
Kind of, yes.
Yes, kind of soluble. Okay. So the next question will be, you also claim that the safe way to operate the hollow fiber membrane bioreactor is below critical flux.
Yes.
Yeah. But apparently this critical flux is very low. Yeah? Even you already increase to, let's say, median flux, it's only about 14.7 liter per meter square per hour. So what will be the suggestion to improve the performance and overcome this problem? Because I think the volume of the wastewater is very high compared to this flux.
Yes, ma'am. The thing is that we didn't do the critical flux analysis because of the time constraint. It needs stepwise process. For example, we could able to achieve the high flux, operational flux, which is above the critical flux. That's why the falling is happen there around 57 LMH. And we choose the very low initial flux just to justify that at very low initial flux, the permeation is good. And then again changes it to median flux around 15 to shows that even at increasing 2 or 3 times, 4 times around from the lower to the median, we could able to achieve similar results. Although the critical flux analysis needs some time, which is one of the future recommendation that we need to come for the real wastewater treatment or the dissemination into the real world scenario. We need to do more operational parameter analysis majorly on the critical flux to check until which point or extent we could able to exceed our flux, initial operational flux in terms of critical flux.
Okay, I agree with you that we need to still do further research here to improve the initial flux. I don't think that maintenance washing the membrane will be a big problem if it's not done very frequently, but we need to have a optimum condition.
Yes.
I think my question is done, but
Maybe any other question?
another question. Okay, the last question then. This will be my last question. In the abstract of your dissertation book, you claim that the conventional process to treat the azodized wastewater is slow
Yes.
process, yeah, high sludge generation, and high operational and maintenance costs. Dr. Wiratni already addressed the cost. I would like to address the slow, the rate of this process. How this process innovation in your dissertation resolve that problem, the slow rate of this conventional process.
So a conventional process usually take significant time for the startup itself, but from our that's why it's slower. For example, if we talk about USB or ASBR, kind of like a flow blanket, sludge blanket, it needs 3 times more time in comparison to membrane process, because membrane could able to, for example, biological membrane, as we see in our result, could able to make a biofilm like barrier, first barrier and a second barrier membrane itself. So the process of the decolorization is achieved from the very initial point in comparison to other kind of anaerobic studies. And when we integrate with the aerobic, we could able to achieve much more results in terms of the pollutant removal as well as the starting point, the start.
So in general, can you say in number, quantitatively, how do you process, how is your process accelerating this overall wastewater treatment process? How many times it accelerate the process?
At least 3 times.
3 times.
3 times.
That's quite good achievement. Thank you.
Okay, thank you, Professor Pena. Next, please, Dr. Ahmad Zainal Abidin.
Thank you very much, Mr. Chairman. I agree with you, Mr. Syed, that textile industry has a lot of liquid waste that create problem to the environment. And I'm glad you do research to overcome that problem. But I'm still not quite clear with your statement. Textile industry is such huge waste. If I look the result from your research, the speed of processing the waste is quite low.
Yes.
Is that you have the same feeling what I feel as well? Or what is it?
So the speed, like HRT, is
Right.
much more higher when we provide the very high initial flux. That's why to overcome this, first we reduce it, but we still at least the lower initial flux, just to check the first major analysis, just to check the mitigate the falling on the membrane, but we still provide the same HRT to match with the HRT parameter. But when we go with the median initial flux, we could able to achieve very negligible or no falling at all until the 114 days or 17 days of the continuous operation, as well as there was no need of taking out the membrane and clean it, as we saw in the reactor 1 and reactor 2 sometimes. And also we could able to the starting point, the results are also very good, and the HRT reduced until 16 hours, from 60 hours to 16 hours. So we could able to achieve all the objectives like falling control, as well as reducing the HRT, as well as high degradation, or in NMBR we could able to achieve 80+% of the dye removal, as well as the 85+% of the COD removal. So we overcome this problem actually just stepwise, like very high HRT with very high flux and very high falling, then very low HRT is very low initial flux, very high results, but again high HRT, and then median flux, very high permeation, very high filtration, and higher results in terms of pollutant removal and lowering the HRT, just 16 hours, which is good in terms of like real wastewater, or as well as the real dissemination of the study.
Okay, so you're quite sure that you will overcome the problem better than current situation?
Yeah, yes, by the end of the study.
again, actually, you mentioned specifically into pollutant, yeah. First is about the color, and the second is about the carbon,
Yes.
yeah. And you use first is with the microbial, and second with the filter, right? But I didn't see its performance. For example, if it is only for with filter, what is like the result, and if it is only with the microbial, what is like the result? You didn't show before, yeah? Can you show?
So the system is, sir, integration of biological activity, like biological membrane bioreactor. It's an anaerobic membrane bioreactor. It's a bioreactor itself, as the name suggests, not just membrane reactor. So inside that, we provide membrane module as well as the sludge or the initiation inoculum, so that both of these work simultaneously at the same time, like forming a film on the membrane surface and like a barrier, initial barrier, and the second barrier is the membrane itself. So taking out results from each is a bit difficult. Like just we need to again put a batch reactor. The batch reactor itself gives that result, because in batch reactor we didn't put any membrane, just we took the anaerobic sludge. So the anaerobic sludge itself has the microbial activity, just microbial activity. That's why in the 300 ml of the small scale batch reactor, we could able to achieve the 85% of the decolorization as well as the COD or the organic removal within 24 hours. But we could not able to scale up for the real world scenario. So we need to come up with the integration of some system which should be continuous in mode.
Yeah, the interaction between the two can be positive, can also negative.
Yes.
In your case, if the microbial flocculant is high, then the membrane is locked.
Yes, sir.
Is that right? So, in the combination of the system, is it going to be positive or negative?
More positive, because we achieve good result without any falling with a dynamic kind of biofilm present. Like the thickness of the cake layer is not that much.
Okay.
When we provide like median flux, and still there is biological activity without any falling. So the membrane itself works and goes for a longer operational period without fault, without need to clean several times with chemicals, and without degrade its quality, and without constraint on the economic side of the membrane itself. So we need to come up with the consortia, like simultaneous effect.
So you optimize with the situation of 14 point something, yeah?
Yes.
Is it the best, or is it the optimum or the best result you get?
It's the best result in our case we get.
Okay. Secondly, regarding the color, yeah, I want to know basic thinking, how the color come up actually.
So the colors will come up because of the presence of chromophores. Chromophores, like azo bonds itself, perform the chromophores, which impart the color to the dye itself, or the dye when dissolved in the water itself. When this azo bond dissociate, the chromophores bond dissociate, then the color itself disappear, because it holds the coloration. And further, when such system works, then because of after the dissociation of such chromophores or chromophoretic azo bond, we got the more toxic intermediates that show, like naphthalene based or aminobenzene based intermediates that needs to be further treated or degraded, that we could able to achieve in our NMBR as well as the aerobic system. So we could able to achieve less toxicity as well as the high color removal and the organics.
Which one is determined? Is it the breakdown of the molecule, or is it the shifting of the frequency of the
breakdown of the molecule shifts the frequency itself when we do the UV-Vis analysis. Like there is shift, if you see in the like UV-Vis analysis, that's 597 nm, there's a shift in the frequency toward the down. So the azo bond dissociates and form other types of like chemical compound, and the color imparting chromophores is also like degraded.
Because in your writing,
Yes.
you only mention about decomposition, right?
Yeah.
Not talking about the shifting of
Shifting, you could see in the UV-Vis spectral diagram, like there is a high the wavelength, at 597 LMH, and 597 nm, and which impart the color. You could see from UV-Vis analysis, which reduce when we done such anaerobic and aerobic activity process.
Okay, thank you. I quite curious with the intermittent process. Yeah, I got feeling that it is contradictory with the activity of climatization normally. Acclimatization. So by intermittent, how the microbial can acclimate themselves, or then they work for what you want.
So if from this graph we could see that there is a shift here when from the same wastewater came into the DHS column, there is a shift. Without aeration, these all are still available, like the aerobes. Okay, but we check the activity on two different parts, like DHS with aeration at middle section, DHS with aeration at bottom section. So the aerated molecules or the aeration will trap in the sponge somewhere in middle of the section. That's why the concentration of such aerobes are much more in the middle section. That will further degrade the dye color as well as the intermediate form. So they will acclimatize by itself in according to the environmental condition or they are given, like anaerobic, then aerobic. For example, in the lower system, just this thiobacillus is too much, but all other are again lesser in the concentration. It is maybe because again anoxic condition maybe happened here in the very bottom of the reactor itself, the DHS column.
What I'm saying is normally microbe need acclimatization for they can work properly. Yeah? But now at the intermittent, the change is so fast.
So before starting both the reactors like anaerobic, aerobic, we acclimatize our system with the aerobic sludge and anaerobic sludge. So we already provide a stage where there is a significant number of the microbe present in our system. But when we continuously provide the aeration, like intermittent aeration, again the shifting changes, and we could see the shifting at different parts of the column itself, which shows their activity, like aerobes activity as well as SRP's activity. So acclimatization will happen before and it is maintained throughout the operation.
So how you can challenge the concept, for example, do with the anaerobic first and then go with the aerobic?
Yes.
Because you find that you are better than the system before.
The reason to done anaerobic first and then aerobic, not aerobic first and then anaerobic, is that because it is already proved or established that for di-azo dye or azo dye wastewater, to dissociate the azo dyes, we need to first cleavage the reductive cleavage of the azo bond itself, which only happened in the anaerobic condition only, or significantly happened in the anaerobic condition only. And further, when the evolution or the generation of the intermediate byproduct, it could not able to further degrade in the anaerobic condition. So we need a slightly aerobic condition again. Or we could see this highly mineralized product when we exceed the HRT, like the contact period of the microbial anaerobes, again too much with the dye stuff itself. But it exceed the as you talked about, it exceed the operational cost and period as well as everything. But in the last stage, we integrate anaerobic and aerobic because of the itself established the previously established study that azo dye needed simultaneous or sequential anaerobic aerobic treatment for the total dye mineralization.
Then I want to clarify as well. You use the microbial that energy need, yeah? Need energy for.
Yes.
Yeah. But energy can be from like sugar or other carbohydrate.
Yes.
But also from the temperature.
Temperature could be, but the effect of temperature on the membrane system
Right.
is
And then also light.
could be.
Yeah.
But
Why
yeah.
in your experiment there is none of two you try to explain this that it is energy data.
First of all, the major aim of the study is not based on the temperature side or the energy side. For example, there are AOPs, the oxidation process, like advanced oxidation process, in which we used like UV, another kind of energy. But the economic side is much more. In that case, we need to set up such technology which is lower at the side of economy and greater at the side of the potential, the pollutant removal potential. So that's why our system is much more efficient and lower at the side of economy. That's why we didn't go for the further providing external source of light energy or some kind. Maybe in that case, it is a very good suggestion. We could use it, but in that case, maybe the microbial consortia again change, which is much more like electron donating or accepting kind of microbes in that case. And it's a good suggestion actually.
Yeah. Because I got product, one of the precaution is don't expose to the light. And also don't expose to the high temperature.
Yes.
Because they need energy for doing something. Okay. You haven't mentioned in the next suggestion, yeah? Okay. And this is the last question I want to have your view as well. The process you develop, actually, like the conventional thinking, yeah? You remove pollutant from one place and places in other place. Okay? But the current thinking, the trend is changed now. Okay? We use the circular economy.
Yes.
Okay? I haven't seen in your suggestion there, yeah?
Yes.
That you also want to introduce such thing in the next future, because the word trend now is with the circular economy.
Yes.
Not to demolish or something, but change to something which is useful and making the economy circular.
Yes, sir. It's a very good suggestion. Yeah, like resource recovery or something. That kind of things. That could be next stage of the research, like how we could able to resource recovery for like in real wastewater there are significant amount of like salt also present that we could able to recover using the membrane technology itself and other kinds of. The aim of this research is more surrounding toward the falling control and the increase the decolorization and as well as the organic removal, which is still the challenge. Before going toward the higher side, we need to come up with some effective solution for the everlasting problems like decolorization. So this research is majorly based on such primary as well as the more important aspect of the time wastewater treatment. We could able to achieve resource in terms of like circular economy, and it could be a future recommendation.
Yeah, why I say this, because industry normally waste processing is a burden. Yeah?
Yes.
It's cost only. Yeah.
Yes.
If there is no such what is it from government, yeah, regulation or something like that, yeah, then they will not doing it. Yeah,
Yes,
okay. But if you a way to process the waste is changed with the circular economy, they might no longer have such or the burden, yeah,
Yes,
to do the testing.
Yes. You're absolutely
Change
right.
the mind and attitude toward that economy circular. Yeah?
Thank you so much.
Okay. Thank you, Padri.
Thank you so much.
Okay, thank you, the examiners. Next, we continue question and comments from the supervisors. We please Dr. Helen to give your question.
Okay, thank you, Mr. Chairman. Hi, Syed. So I would like to congratulate your presentation today, and I have several questions for you. The first one is, I think it is very important to highlight what is the difference between the synthetic wastewater and the real case or the industrial wastewater that are gonna face by this kind of technology if it is applied in the real case scenario. And then after that, if this technology is being used in the real industry, can you please describe? Will you expect to have like similarly promising results? And maybe you can also explain about the challenge that may arise during the applications.
Thank you so much, ma'am. So yes, there is a not too much significant difference between synthetic and real wastewater because we mimic the chemical compositions and then which is present or the concentration in the real wastewater itself. So, but right now we are also doing in our lab the real wastewater treatment studies, and with the similar with the NMBR and DHS. And preliminary studies gives us around 63% of the organics and around 70%, above 70% of the decolorization also with the real wastewater. But it's just a preliminary study right now. We need to go with a further extended time period to check like it's the same or there is some operational parameter we need to check upon. And the constraint right now we are seeing is the high sludge still is present in the real wastewater, which need to be like, because high sludge will fall the membrane itself too quickly. So we need to again come up with an optimized operational parameter, like critical flux, and like we are doing this research.
Okay, so talking about the operating condition that you are going to optimize later on, maybe you can also explain about how operation condition may change the performance of your ANMBR technology. Yeah, for example, maybe you can also address about the HRT or maybe about the membrane area, because that will directly influence the amount of wastewater that you can process in the same time frame.
Yes. So yes, the several things need to be done. For example, checking upon the membrane area, like how the more the module, the number of fiber we used, we could make have more permeate in more flow rate. We could able to optimize the flow rate, as well as the like HRT. HRT is one of the major operational parameter. Like we should not go beyond a certain HRT. It will not give an economical aspect or something. That we prove using our current synthetic textile wastewater treatment in whole fiber submersion NMBR. So with the real wastewater, we could able to optimize the similar lower HRT around 16 to 17 hours, but we need to check on the permeation from the membrane itself, like and also to check the falling itself, like what parameter which enhance or decrease the falling on the membrane, and these could be taken as like HRT, the temperature and pH also. Like temperature has some effect, but it's not too much effect on the falling side.
Okay, you mentioned you done the experiment with the real wastewater right now, right? For how many days has it operated?
It's around 15 days.
15?
15.
15 days, okay. 1-5.
Yes.
Okay. Do you notice any fouling during the period? And can you please compare it with the results from your synthetic wastewater?
So yes, we found not too much falling, but we could see that the fallen particle itself started to accumulate on the membrane surface by the end of around 10 days of the study, and the flow rate or the permeation rate is becoming slow, but not too much slow. We could still able to go beyond like 20 or 25, 30 days around without any need of cleaning. Because the sludge in right now, the wastewater, real wastewater is too much. That is like filtered out by the membrane. That's why it accumulates on the membrane surface.
Okay, yes. So in conclusion, maybe you still need to do like more optimization for the real case wastewater, but the performance is quite good, yeah.
Yes, and also real wastewater, like the parameter like fluctuative. It's not similar like synthetic wastewater, like constant. That's also a problem. Sometimes in batch, the can we got has so much sludge, sometimes not. But we need to, like we are right now doing the critical flux analysis, so we need to come up with the optimal flux, which will give us more period of time for the treatment without any falling or a need of cleaning. So.
Yeah. Okay, Mr. Chairman, maybe that's for me. Thank you.
Thank you, Dr. Helen. Next, please, Dr. Sri Haryati Swardi.
Thank you, Mr. Chairman. Syed, congratulations. You come to this stage. I was wondering about the stability of the product that stays in the sponge surface. Yeah, because I consider that your reactor run in such an extensive time. It's 114 days.
Yes.
Yeah. Is there, do you consider the stability of the dyes that absorb on the surface, the intermediate degradation product that absorb also to the sponge? Do you see any release that possible? Yeah, it could be that it's released to the system during your process. And if they do release, did you see any indication of the effect of this product or the dyes itself?
Under the influence of intermittent aeration, as we could see that the system could able to achieve a steady state in comparison to the for example, this here, we could see, we could able to achieve the steady state in terms of after the 50 days of like the starting of the phase second. So even there is an absorption or the accumulation of the intermediate product on the sponge, we couldn't see from the result any release of the toxicity. For example, from the NMBR, we could see the fluctuation too much. Maybe it's because of the toxicity and the changes of the microbial biofilm on the membrane surface. But in the DHS, we could see that the results are very constant. This blue triangle could show. But there is fluctuation without aeration. So under the intermittent aeration, the ability of the biological activity at different stages of the column stabilize the overall performance and could not allow the toxic byproducts, even if it's absorbed, if it's absorbed. But from my side, I think it's biodegrade under the presence of biological activity into the very mineralized form. So there is no toxicity could be happen from the result itself. We could see. Also, we could see from the stability in the PTCO coloration also achieved after the second phase, like under the intermittent aeration. So that's why the role of intermittent aeration come into the perspective.
Oh, that's the background of the methodology. That's why you put the intermittent.
Yes, ma'am. Under the aeration, the intermediate toxic byproduct degrade much more faster in comparison to without aeration, because they need oxidative degradation.
Because when I'm interested in the word affordable, that mentioned by Ibu Wiratni, is it possible that we extend the intermittent? I mean, you do a longer period of pause. So the aeration consumes some energy, and energy that means cost.
Yes, ma'am.
So would it be possible you optimize the intermittent period?
Yes, ma'am. There is possibility too, because we check like 5 minute off and 5 minute on of our aerator. From the previous research, also like they could optimize like usually around 10 minute off, 10 minute on. So we could check from the further, we could optimize our operational parameter on the based of aeration, like 5 minute on off, then 10 minute on off, like 20 minute on off, to see what's the effect of aeration itself and what is the microbial consortia change at the different sites or the different part of the column itself, the leach's column itself. That will give us much more clear view that the role of microbes as well as the role of sponge itself to maintain the microbial consortium.
Will you vary that parameter when you start with the real wastewater?
Yes, ma'am. Right now, we just still, because it's just a preliminary study, so we still go with the same kind of. Further on, we hope to change for aeration as well as for the critical flux. We are stepwise increase.
I wonder if your real wastewater that you're going to try or you test consists of several type of wastewater, several type of dyes. Because here you only use one type of dyes. Yeah, the RB, the blue. Is your real wastewater consists of several dyes?
Yes, it came from a dyeing industry. It has several kinds of dye.
Which industry?
Dyeing wastewater.
Dyeing? Is it the textile or batik or any specific?
Batik.
Batik. What's the most difficult dyes to degrade in batik?
Usually uses reactive dyes, reactive dyes. Mostly reactive dyes, azo dyes also there.
So you will face both different type of dyes.
Yeah, the coloration is too much in there. Although we get it after anaerobic treatment, it's like a post-treatment we are doing, but still the sludge is too much, the color is too high, and but the preliminary study gives us around 70% of decolorization in terms of UVs, as well as PTCOs are also a bit higher than the national standard, but we could check is it able to curb under the national discharge limit with changing the operation parameter like aeration in DHS and changing the critical flux, like initial flux in the ANM periods.
Okay, maybe this is my last question. I was wondering, if you're going to run with the real wastewater, which one do you think will be better? You use the inoculum from the sludge that's taken from the wastewater treatment plant, or you use the divine consortium that you construct in the laboratorium? I mean, you select and you have the best you have. Which one do you think better?
So the studies which were done with some defined consortia has constrained when we put in our very big scale real scenario. So that in our system, we come with a dynamic type of microbial consortia which stabilize itself with the acclimatization and with the giving operational parameters and the conditions. So in my consideration, dynamics works much more good in terms of when we go for the real scale or high concentration of the wastewater, real wastewater at the real scenario. So using the dynamic kind of like consortia is much more efficient and good in terms of high scale or real scale wastewater.
Okay, thank you. Thank you, Mr. Chairman.
Thank you, Dr. Sri Haryati. The last, please, Professor Chandra.
Okay, I think so. I just go to the practical implication and your future research. So, what is the practical steps needed to implement your system in the textile industries? And also you have to, I think that one, what will be the practical step needed currently, you have already data now, to implement your system for treating the real wastewater?
So for implementing in the real wastewater scenario, like real industry, first of all, we need to do a bit more analysis or detailed study on the optimizing some parameters like critical flux, as well as like HRT fluctuations and other things, membrane surface and pores, like how much membrane we needed for the large scale system without falling. And second, before going to the very real scale, we need to come up with a pilot scale project to enhance the scaling and check other, like the parameter that we took is work in that such big pilot scale implementation or not, or we need much more like changing in the parameter itself or like optimization. Then we could able to go for the real scale textile wastewater industrial implementation. And this system is much more efficient for the MSME, like small scale batik industry or something, for the immediate or the fast implementation of the wastewater treatment technology in comparison to very big scale. Before, like first like optimization, then pilot scale, then MSME, then gathering all the information, we could able to achieve the real scale results, and then we could able to disseminate or translate our technology toward the large scale dyeing or printing wastewater industries.
Okay, so you briefly mentioned about the techno economies. So you can show the data.
Sure.
What is your calculation? What is the assumption to do your calculation for the techno economy aspects?
Okay. So this is the. These are the parameters taken from like previous research also. Some of the parameter like the in influent pumping energy, when we go for the pilot or like large scale, is around this much in previous research, and net flux around this much meter per hour in terms of hour, and affluent pumping energy in kilowatt hour per meter cube is around 0.028, and electricity, that is LE, usually around $0.1 per kilowatt per hour, and the chemical cost for the cleaning is around 0.08, and the membrane life I assumed around 8 years if we go for the like large scale hollow fiber submerged in MBR membrane. And using this OPEX, like operational expenditure formula, I could able to achieve like $0.11 per meter cube of the overall treatment cost in terms of OPEX only, which is lesser in terms of just MBR, which is around $264 per meter cube per day, and for the hollow fiber MBR only from previous research around 0.55 to 0.68, and this one like conventional activated sludge technology is around 0.18, and another one around 0.41, and overall our system just with ANMBR is like good in terms of OPEX if we took such operational parameters.
Okay, so it seemed to be rather promising to
Yes,
to play. Okay, thank you.
Thank you so much, sir. Thank you so much.
Thank you, Professor Chandra. Ladies and gentlemen, we just finished the first session of dissertation defense. And then I will ask your patience to give opportunity to graduate school commission to conduct a meeting to decide the result. Then I will suspend this session for about 30 minutes.
Thank you so much. Thank you so much. Thank you so much.